Okay, welcome to lesson 4. Today we'll be going over chapters 5 and 6, which will cover nested derivations and indirect derivations. These are the last two methods of derivation that we'll learn for our derivation system, but we will get some more rules at some point. So let's start with chapter 5 with nested derivations. So we'll remember conditional derivations, which are where we wanted to prove a conditional statement. So we wanted to prove an if-then statement. To do that, we assumed that the left side of the conditional statement, the if-then statement, which was P, and then we would show through however many steps the right side of the if-then statement, in this case Q. And that would let us say, if you assume P, you'll get Q, or if P, then Q. But sometimes we're going to need more than one conditional derivation in a proof to get at what we're trying to prove. So for example, we might have if P, then if Q, then R. And if we want to show if P, then if Q, then R, well, then we have to first assume P to be able to show if Q, then R. Because that's how we do our conditional derivations. We assume the left side of the if then, like we do over here, and then we get the right side. So if we want to show if P, then if Q, then R, we have to assume P and show if Q, then R. But to show if Q, then R, we would need to do another conditional derivation. In this case, we would need to assume Q to be able to get R. So in a case like this, where we're trying to show that if P, then if Q, then R, we need two conditional derivations in the same proof. So how are we going to do something like that? Well, we'll end up doing what we call nested derivations, where we put one proof inside of another. But before that, let's look at a natural language example that is a bit clarificatory. So if I say to you, if I go to the store, then if the cashier is around, I can buy some orange juice. You'll note that I'm using two if claims. I'm saying, if I go to the store, then if the cashier is around, I can buy some orange juice. In this case, you need to imagine me first going to the store. Then you need to imagine that the cashier is around before you can imagine me buying some orange juice. So yeah, to imagine me getting the juice, we need to imagine first that I go to the store and also that the cashier is around. So there's two hypothetical layers there, right? So let's see how we would do this in our formal system. We would do two conditional derivations, or consider two if-then claims in one argument. So let's say we have the following argument. On the premise R, we can conclude, therefore, that if P, then if Q, then R, right? Because it's on the right side of the turnstile. So we have the premise R, trying to show the conclusion, if P, then if Q, then R. Well, as we said before, each hypothetical layer, each if-then claim, needs to be proved to be able to prove the whole thing. So our derivation will have to have two layers. We'll be nesting a proof inside of a proof. So, well, I'll show you this, and then I'll actually show you doing it step by step. But you can see here we have, we want to show, like always, we write what we're trying to show, if P, then if Q, then R. And we have this premise R. Well, we know from our conditional proofs that if we're trying to show if P, then if Q, then R, we need to assume the left side of this if-then statement. In this case, it's P. So we assumed P, but we still need to demonstrate another if-then statement. So we said, well, we're going to have to show that if Q, then R, because if we can successfully show it, then we can show that after you assume P, you can show if Q, then R. So we say we're going to show if Q, then R, and then we open another proof. So this is where we have our nested derivation. You can see we have two lines here, over here on that one. We have two lines starting there. And this is because we've opened another proof. We've opened another derivation. So anytime you want to show something else, conditional, for example, you need to open another, like, anytime you make an assumption and you try to show something on the basis of that assumption, as we've done here in lines 3 and 4, you need to open another proof inside your proof. You need to nest a proof inside your proof, or nest a derivation inside your derivation. And that's why you can see we have 2 lines deep here instead of just one. Yeah. So then we assume Q, we show R. Well, conveniently, we know that R is a premise, so we can just restate it down here. And then we've done a conditional derivation of this second proof, this nested proof. You can see we've put it here. It closes this proof we've opened. We've shown that if you assume Q, you get R. So then we've shown this claim, if Q then R. So we can close the initial proof we tried to start with, because we showed that if you assume P, you can get this thing that we showed on line 4. So we can close our final conditional derivation. We can close our final proof, and we can show that, well, if you assume P, and then you also assume Q, you can get R from assuming Q, which means that you can get if Q then R from assuming P. And so then we have our nested derivation. So you can see this is a bit complicated, these layers of derivations, these layers of proof here. But as you get practice, again, I promise it'll be easier. I'll show you one right now, and hopefully that will help. And I will show you a bit more shortly, but we're just going to do one for now. Yeah, okay, so let's do that. All right, so you can see I've opened the practice document. You'll find it on Brightspace like normal. And I will now show you how to do a nested derivation. We'll do a few more examples later, but we'll just start with this one. So you'll notice this is the exact same argument that we were looking at in the slide that I was just showing you, but I'll show you step by step, and hopefully that will make things a bit easier. So as always, we're going to write what we're trying to show, which is the conclusion. So P, if P, then if Q, then R. There you go. I always like to list my premises, even if I have to do it again. And we always have to make sure we indent under our show. Under our show line, we always have to indent with a space bar at the beginning of each line. And then, yeah, so what are we trying to prove here? Well, we're trying to prove if P, then if Q, then R. We'll notice our main connective here is a if then, so we have a pretty good idea. We're going to do a conditional derivation. So we will assume P. Great. So if we assume P, we know we need to show if Q then R, right? So how are we going to do that? Well, we know that we need to show another if then claim. So we need to do another conditional derivation, right? So we're going to start a new derivation. We're going to start a new derivation by putting in a show line. We're trying to say that we're going to show something. In this case, we're trying to show if Q then R. Because if we can show, after assuming P, that if Q then R, then we can show that if Q then R follows from P. And we can show this. Okay, so now we're going to make sure we indent twice. You hit space bar twice. And we're going to do that because we've opened another show line. We've opened another derivation, another proof, right? And every time you open a new proof, you have to add another indent. Well, we're trying to show a conditional on this new nested derivation. So we're going to assume the left side of the conditional. We're going to assume Q, right? And we need to show that R follows. Well, we know that R is a premise already, so we have access to it. So we're just going to use it here. R we have as a premise. So we'll hit enter. You'll notice now that after assuming Q, we've shown that R can follow. So we can close this conditional derivation. So we can close the nested derivation here. We can't close the whole derivation because the whole derivation is about this, right? But we can close this nested derivation that we've put inside the bigger derivation. How did we do it? We did a conditional derivation, CD. We know that we're talking about this one because it's the one that is closed on this level, because you can see before it there was a double indent and now there isn't. So we know we're closing this proof. And how did we show, what line did we show that R could follow from Q? Well, we showed it on line 6. So you see over here, this becomes good. It's happy with us. We've closed the proof. Well, great. Because we closed the derivation that we started here, we now have access to this on line 4. We have access to if Q then R. And we were trying to show that if you assume P, then you get if Q then R, right? So we can finally close this line up here, what we started with. And how did we do it? We did a conditional derivation. And we showed on line 4, because that's where we have this information that we eventually proved. You can't cite this until you prove it, and we did here. You can see we closed the proof for it. We showed on line 4 that if Q then R can follow after you assume P. So we write that we have closed a conditional derivation on line 4 because we assumed P and we got if Q then R, and you can see the system likes that. It gives us a check mark. So that's the idea. We'll do some more examples soon. It's hard to wrap your head around at first, but if you read the chapter and watch my video and watch me do a bunch of examples, and hopefully you do them in the problem sets and stuff, it should be all right. All right, so let's consider some more information about our nested derivations. So we know that, on anytime you do a new line in a proof, you have to tell us what you're doing or where you're getting the information from. So for example, on line 2 here, you cite where you got R from. It's from a premise, right? Because we have R as a premise up here. But there are some rules around what you can or can't cite in a proof. So at any point in a proof, you can only use information from before the line you're at, and which is not from another closed proof. Or you can say you're going to show something or assume something. But if you're citing justification for a line like, oh, I got this sentence from a different line, it has to be from a line previous to the one you're entering, or and it can't come from a closed proof. So, for example, in this case, which we have been looking at, on line 8, if I wanted to, which would be weird, you wouldn't want to do that, but on line 8, you couldn't cite something from line 5 here, or line 6, because you can see it's from a proof that's already been closed on line 7. But you could cite something from like line 3 or line 7 itself, because you'll see like they're not from a proof that's already been closed. And you can tell this by the indent layer because there's only one indent, whereas this nested derivation has 2 indents. So we don't have access to the lines that have 2 indents because that proof has been closed already. So just keep that in mind. You can only use information from before the line you're at, and which is not from another closed proof. Now you'll remember our direct derivations, where we were able to show that something follows directly from somewhere else. Well, we can do these nested in other proofs as well. So for example, oh, well, there's an error here, but you can see what we're trying to show down here. So for example, if you have Q and you're trying to show if P, then not Q, then not Q, we're going to need to use our double negation introduction rule eventually, or double negation rules, to show directly that something follows. So you'll see, for example, we start on line 2 with Q, and then we would assume if P, then not Q, because remember from this, we are trying to show not Q, which is a mouthful. But yeah, you'll assume if P, then not Q, and then you want to show not Q. And then in this case, you're going to use double negation introduction on this Q we have from our premise. So you have not Q. You'll apply double negation introduction again on line 6 here to line 5, and then you'll get not Q, because you can use double negation introduction to add 2 negations. And then you've shown directly through our rules of direct derivation that not Q follows after you assume if P then not Q. So there you can see we've used a direct derivation there to get to our conditional derivation, which is where you show that if you assume if P then not Q, you can get not Q with the premise Q. Okay. So that's a little confusing too, but just know that you can use all kinds of derivations as nested derivations. So if you need to open another proof somewhere for some reason, you can and then nest a derivation by opening a new derivation or a new proof. You can use your direct derivations as well. Okay. So these are some formal definitions of nested conditional derivations and nested direct derivations if you need them. These are from the textbook. You can find them there. I think they're a little wordy. I just like to learn the skills to kind of wrap my head around it. But these are like formal, strict definitions, which you might find helpful or useful. So a nested conditional derivations is a sequence of assertions aimed at showing some statement if P then Q, or some if then statement. You can replace P with P and R or something, and you can replace Q with Q and S or Q or T or something. Okay, but a nested conditional derivation is a sequence of assertions aimed at showing some statement if P then Q, beginning with an assumption that P, in which every assertion after the first is justified. So in which you assume P, and then afterwards you justify the next lines to show Q, either because these are the sources of your justification, either because the thing that you've added is a premise of the argument, it's the conclusion of a rule of direct derivation applied to previous assertions, or it's listed next to a show line that contains a complete derivation. So if you do a show line, you close that show line by doing a proof. Now you have access to the stuff on that show line. Okay. Similarly, here's the formal definition for a nested direct derivation, which is in this case a sequence of assertions aimed at showing some statement P. It could be P, could be P and Q, could be Q or R, whatever. So a nested direct derivation is a sequence of assertions aimed at showing some statement P, and every assertion in the sequence is justified either because it's a premise, it's the conclusion of a rule of direct derivation applied to previous assertions, which are available, or again, it's listed next to a show line that contains a complete derivation. And again, you do a show line, you do a derivation, a nested derivation, and then you have access to the thing on the show line. All right, so let's do some more examples, and hopefully this will all become a bit more clear. All right, so let's do some nested derivation practice. You can also, of course, go to the problem set. You'll want to do the problem set, of course, as always. That's in chapter 5 for nested derivations. So make sure you do that. But here I'm just going to show you some examples. You can find the same examples on the practice document. So yeah. Okay, so let's start with this one. So as always, we're going to write what we're trying to show. It's Q. And then let's list our premises like normal. And I will copy and paste this one. Okay. Actually, let's get rid of these outside brackets. Let's abbreviate it, following our abbreviation rules, getting rid of the outside brackets, so that it looks a little cleaner. Okay, so we're trying to show Q, right? Well, to get Q, we are going to have to get if S then R. Because we know that if we can get if S then R, then we can get Q, right? Whatever is on the left side of an if then, we can get the right side out of it if we can get the left side through modus ponens. So let's consider how could we get if S then R? Well, that's a conditional derivation. So let's show, we want to get something else here that we can use. We want to get this that we can use. So let's show if S then R. Oh, and I forgot to indent all of these, of course. Make sure they're indented properly. And then under the show line, you need to put another indent because you've opened a new derivation, a nested derivation. So we assume S. Conveniently, we have R as a premise already. You can see up there. So we can put R. So we can close this nested conditional derivation, right? We've shown that if you assume S, you can get R. So put conditional derivation, line 6. You can see it likes that. So now, because we've closed this derivation, we have access to if S then R. On this show line, we have access to it. Great. So now we have if S then R. And from our premises, we have if S then R then Q, right? So we can use modus ponens. Because, of course, this is the left side of this whole statement. So we can get Q by modus ponens on line 4. Now that we've closed this, remember, we have access to it. So we can get if S then R, and we can use that from our premise, with our premise here, to get Q, right? So modus ponens on lines 3 and 4. Then finally, you can see we wanted to get Q. We have Q. And because it's here in our proof, we don't need to like use some special derivation. It's just a direct derivation on line 8. And you can see, there we go. Works well. All is good. All right. Let's do another one. What looks interesting? This is the one I did earlier, I showed in the video, so we can skip that one. Let's do number 2. Why not? So, as always, we want to show Q, so we list that. And then we can list our premises. So we have P as a premise. You can see this is a premise. We can see that this is a premise. Great. Of course, remembering to indent under this show line. Great. So we want Q. How can we get Q? Well, let's look for where there's a Q in our premises already. There's a not Q here. How can we get that not Q to get us a Q? Well, if we can take this if-then claim, then we can get a modus tollens, right? If we can get a not R, then we can get a not Q, because we can use modus tollens. If the right side of an if-then is negated, we can get the negation of the left side. So if we have a not R, we can get a not Q, right? And then if we can get a not Q, finally, we can use our double negation elimination to get rid of 2 negations, right? So we could just get a Q. So let's see, how could we do that? Well, from P, we have if P, then not R. So conveniently, we have not R from modus ponens on 4 and 2. Great. From that, we can get we can get not Q, right? Because now we can do modus tollens with this not R and this claim here. So we put 5 and 3. And then finally, we can get Q from double negation elimination on line 6. Well, I guess this one didn't have a nested derivation, so sorry about that. But it is good practice nonetheless. So, there you go. So we can get direct derivation line 7. Good practice nonetheless, but it doesn't have a nested derivation. So hopefully the next one will. So let's do that. Yes, that's good. Let's just clean this line up. So you'll see I copy and pasted the conclusion we're trying to show. I like to list our premises, not T. Sometimes I type them out, sometimes I copy and paste them. Oh, forgot to say that that's a premise. And remember, you can use various ways of typing the symbols that you'll find up here. Yeah, let's continue our. So we've listed our premises. So we're trying to show a conditional, right? The main connective here is a if-then. So we're trying to show that if you assume P, you can get if Q, then you can get if Q, then R, right? So let's start by doing that. Let's assume P. And we want to show, right, if Q, then R. Because we assume the left side of this if-then, and we're trying to get the right side. So great, now we have a nested derivation, right? We're trying to show if Q, then R. So let's assume Q. And now we need to show R somehow, right? To close our conditional derivation. All right, so what can we do? We're trying to get a R at this stage. Well, from this premise, we can see that if we have a T, then we can get S arrow R, and then if we have a S, we could get an R, right? So how could we get a T? Well, conveniently, on the assumption that Q, we can get not Q, right? By double negation introduction on line 7. And this will be useful for us for this line here, right? You can see there's a not Q on the right side. So we can get a modus tollens and get double negation T, not T, right? Because if we have this side negates the right side of this if-then, so we can negate the left side as well through modus tollens. So we can get not T by modus tollens on 8 and 3. Perfect. Which means finally that we can get a T by double negation elimination on 9, right? Because we have 2 negations here, we can always eliminate that. Well, with that, we can get our S then R, right? Because on line 4, we have this if T, then S, then R. We can use modus ponens to get S, then R, using modus ponens on 10 and 4. See? Going well so far. It's a bit long, but it's going well so far. So now we want to get an S so that we can get our R, right? Because we're trying to show if Q, then R, so we assumed Q, we want to get R. So how can we get an S? Well, if we go back to our premises, we'll see if P, then S. And conveniently, we also assumed P, right? Because we're trying to show that if you assume P, then if you assume Q, you get R. So let's get our S by modus ponens on line 2, if P, then S, and 5, where we assumed P. All right, so now finally we can get our R from line 11 here. So we can put R, modus ponens on 12 and 11, you'll see there, which is great. Now we have our conditional derivation. We're trying to show if you assume Q, you'll get R. We assumed Q and we got R. So now we can close this nested derivation, a conditional derivation, because we showed a conditional claim, an if-then claim. We finished it on line 13. So you can see it's happy, it's a check mark. We now have access to this if q then r. Well, we already assumed p up here, right? And we've already shown if q then r by doing this whole nested derivation and closing it. So now we can just close the whole thing. We did another conditional derivation. We assumed p, and then from that, we're able to show q then r. You know, we're trying to show this whole if-then statement. So we got our, after assuming p, we got access to this q and r. So we can cite it from line 6. And there you go. Again, here it is, a big complete proof. Again, it seems very complicated. If you do the practice, do the examples, you know, it will help you. As always, I recommend you do this on pencil and paper and then put it in the system and check and go back to pencil and paper and all that. Yeah, okay. Let's do another one before moving on. Let's do number 6 here. So as always, we write what we're trying to show. In this case, I will copy and paste it, and I like to get rid of the outside brackets so it's less messy. And then we list our premises. As always, doing the right amount of indents, keeping an eye on that. All right. So what are we trying to prove? Well, again, we're trying to prove a conditional. In this case, we're trying to show that if you assume p, then you can get not s then r. So let's assume p. And we are trying to show not s then r, right? After you assume p. So let's do that. Not s then r. And now we've opened another derivation by having this show line. So we indent twice until we close it. How do we show this derivation? Well, again, it's going to be conditional because it's an if-then. So let's assume the left side, which is not s this time. And we want to get an r out of it, right? Okay, so now let's look for where we're going to get an r. Well, you can see on line 2 from this premise, if we can get a p, then we can get a q then r. And so if we can get a q, we can get an r. Well, let's start with this. So first we know that we can get if p, then q then r. We already have a p by assumption down here. So let's modus ponens that and get us a if q then r. Modus ponens on 4-2. Great. Well, now we want to get an r still. How are we going to do that, right? Well, we're going to have to get a q, so that maybe we can modus ponens it, right? Luckily, we have this not s by assumption, and we have this line here. So if we modus tollens this, because we have the negation, we can get not q. So let's do that. Modus tollens on line 6 and line 3. Great. And we still want to get this q. Well, nice, we have a not q, because now we can get a q by double negation elimination on 8. Which means, finally, we can get our r through modus ponens between this q and this if q then r. R by modus ponens on 9 and 7. Great. So now we've shown this thing that we were trying to show. We've shown that if you assume not s, you can get a r. So we can close that conditional derivation on line 10. That's where we got the r, which means we now have access to this if not s, then r on line 5. Well, we already assumed p, and we were trying to show that if you assume p, you can get not s, then r. So we can close our last step. Conditional derivation, citing line 5, which we now have access to. And there you go. Just like that. Is there any others I want to do? I think that's probably good. You probably get the idea. Let's do number 7, because it looks like it has lots of indented indented things and would be a good example. So we're trying to show S as always. Let's show the conclusion first. Put an indent. We're going to list our premises. I don't like the outside brackets, so I'm going to get rid of them. Technically, it's okay, but I like abbreviating them. We have P, then Q as a premise. We have Q, then R as a premise. Great. So how can we get a S? Well, if we have P then R, then we can get S, right? So how can we get P then R? Well, if we assume P, well, first let's say we want to show if P then R, right? Because if we can get if P then R, then we can get S by modus ponens, right? If we have the left side of this arrow here, then we can get the right side by modus ponens. So we want to show if P then R. So we open a new derivation, indenting twice as always when you open a new one. Okay, so how can we do that? Well, we assume P, and then from that, oh nice, we get Q, right? By modus ponens on 6 and 3. Line 6 we have P, line 3 we have if P then Q. And then conveniently from this Q, we can get R, right, by modus ponens again. So R by modus ponens on 4 and 7. And that's great. So we wanted to show if you assume P, you get R. We've shown this. We can close our conditional derivation, which gives us, sorry, on line 8 we got it. So now we have access to this on line 5, right? We have if P then R. Well, we know that if we have if P then R, see it's on the left side of this if then statement. If we have P and R, we can get S. So we can get S by modus ponens again on line 5, which we now have access to, and line 2. And look, there it is. We've shown S. It directly appears in our proof. So there you go. Now we have a direct derivation of S on line 10. And look at that. All good. There you go. Okay, so now let's get back to the indirect derivations that we'll be seeing. Okay, so that's the basic of nested derivations. So now we're going to add one more type of derivations. This is the last one, is indirect derivations. This is in chapter 6, which you should be doing the reading on as well. And these derivations are, so in direct derivations, we would pull something from the proof that's stated, that we showed, and we would say, there it is, direct derivation. With a conditional derivation, we would assume something and then show that something else followed from it. You know, we would say it was conditional on that. And now for indirect derivations, what we're going to do is show that if you assume something, you run into a contradiction. And so what you assumed cannot be true. So this is going to show that what you assume is not true. So I've called it here a proof by contradiction, which means you prove that something is true because its negation leads to a contradiction. So for example, you might show that believing something P leads to a contradiction, and so you get not P. So here's a case to get your head around it. Imagine your older sibling wakes you up and says it's time for an important exam and that you've overslept. You start frantically getting out of bed, but when you look outside, it's still pitch dark, and then you look at your phone and it says it's only 4 a.m. So you know in that moment that it can't be time for the exam yet. The pitch black outside and the 4 a.m. on your phone shows you that what your older sibling was saying is not true. It's not time for your exam yet. You have not overslept. And that's because the new information you have contradicts what your sibling told you. It means it can't be the case. Turns out your sibling was just pranking you. So we'll be doing something similar. So, we'll assume something, in this case Q, let's say. We'll show that it leads to a contradiction, in this case P and not P. And then we'll know that Q can't be true, so we'll get not Q. As always, the P and the Q here could be anything. It could be like, we assume Q and S, and then that leads to a contradiction, both T and not T. Or it could be we assume Q or R, and this leads to a contradiction, both not if P then T and also if P then T. We just need a contradiction. So we need something and its negation to get the contradiction. Okay. So we could prove that the following argument through indirect derivation if we want. So we want to show not P, and our premise is if P then not P. So what we would do, and I'll show you on Carnap, what we would do is, of course, we would always write the right side of this. We would list our premise, of course, if P then not P. And now we want to do the indirect derivation. Well, we're going to show not P, we're going to assume P, right? And then we'll show that it leads to a contradiction. Well, in this case, we can use modus ponens on lines 2 and 3 to get not P, right? Because if you have P, then from our premise, you have not P. But P and not P are in contradiction. So we can get not P by indirect derivation. So we close our proof here. We cite the contradicting lines 3 and 4. And this tells us that we have got not P by an indirect derivation down here. So there you go. Simple enough concept. I will show you this now, step by step. Okay, so here we have our first indirect derivation. So we're going to, as always, show what we're trying to show. We will list our premise. In this case, there's only one. And then how are we going to get this not P? Well, with our indirect derivation, if we show that P leads to a contradiction, then P can be true, and so we get not P. So let's assume P. Well, after assuming P, you get not P by modus ponens. And that's 2 and 3 together. And then you can see we have two contradicting lines here. Line 3 has P, line 4 has not P. And so if you assume P, you get a contradiction. And so we know we get not P, so we can close our indirect derivation, citing the lines that are in contradiction. And that shows not P. So if this was part of a larger proof, we would now have access to not P, for example. All right, so again, here's a formal definition of indirect derivation if you need it. Again, I prefer to just get my head around things, do some practice, get some examples shown to me. But this is in the textbook and it works if you need this kind of thing. So yeah. So indirect derivation is a sequence of assertions aimed at showing a statement P is false or that not P is true. And of course, P and not P could be replaced by anything as always. You do this by beginning with an assumption that P is true, and then you do a bunch of lines that are all justified. Every assertion after it is justified by all of the normal reasons, and which leads to a contradiction, and so therefore shows that not P is true if you assume P and it leads to a contradiction. Now you can also use indirect derivations inside other derivations. So if you want to prove that with the premise if P then Q, you can get if P then not Q, therefore not P. You will end up using an indirect derivation, as you can see from this picture, and you can see it's nested. And I will show you that now. I will do this step by step instead of going over it like this. All right, so here on the same practice document, we have the example we were just looking at, and let's go through how to demonstrate it. So as always, write the conclusion we're trying to show. I like to get rid of the brackets. And then I like to list our premises. In this case, it's a P arrow Q. All right. So you'll notice what we're trying to show is a conditional derivation, right? Because the main connective is this if-then arrow. So what we're going to want to do is assume the left side of it, right? And then we want to show not P. Well, how are we going to do that? We could do an indirect derivation. We'll show that if you assume P, you get a contradiction, right? So let's assume P. Yeah, so we assume P, and then we can get both Q and not Q by modus ponens, as you can see on lines 2 and 3. So we'll get Q from modus ponens on line 5, where we assume P, and line 2. And we'll also get not Q from modus ponens on line, let's see, what was it? 5 again, right? And line 3. But if you'll notice, you assume P, and then you get a contradiction out of it. You get Q and its negation, not Q. So we know that we can get not P by indirect derivation. So we'll cite the lines that are contradicting each other. We've closed it, everything is good, and now you can see we have access to what's on this show line, just like we did with our nested derivations. I mean, this is a nested derivation. This is a nested indirect derivation. So now we have access to this, which is great because now we can close our conditional derivation, because remember what we were ultimately trying to do was assume if P then not Q and show not P. Well, we assumed if P then not Q, and then we were able to show not P by indirect derivation. So we can now close our conditional derivation on line 4, where we got what we were trying to show. There you go. So that's one example. Okay, so before continuing on with some further examples, I just wanted to revisit our 3 derivation types that we've now seen. So we have direct derivations, where we use our rules of direct derivation, which so far include modus ponens, modus tollens, double negation introduction, and double negation elimination. And then you produce whatever you're trying to show using those rules and the premises you already have. Then we have conditional derivations, which allows us to prove a if-then claim by assuming the left side of the if-then claim and then producing the right side after the assumption has been made. So, I put it like you show if P then Q by assuming P and then producing Q after the assumption of P has been made. And then we have this third type of derivation I've just showed you, which is an indirect derivation. And that's the proof by contradiction I was saying. So you would show not P by assuming P and then showing that a contradiction, say Q and not Q, follows from assuming P. All 3 of these can be nested. I'm actually going to write that because it's so vital that you can put all these in a nested proof. You're going to have to excuse my handwriting here with my mouse, but this is a big deal. Nested. And I'll put 3 here. So all 3 of these types of derivations can be nested. They can be nested. We've shown proofs with 1 nested derivation, but there can be as many as are needed. But yeah, all 3 types of these derivations can be nested. So keep that in mind. All right, now let's do some more examples. All right, so more examples of indirect derivations, again, as always, on the same practice document that we've been looking at the whole course today, the whole lecture today. So let's start with question 2 here. So as always, we write what we are trying to show, then the premises, then this other premise that we have. All right. So we want to show not P. Well, in this case, we can use indirect derivation because we can see that, well, if we have P, we're going to get a contradiction. You can tell already by the modus ponens that could be done here. So let's assume P, then we get Q by indirect or by modus ponens on 2 and 4. We get not Q by modus ponens on 3 and 4. And then we get our indirect derivation. We assumed P. We got 2 contradicting things on line 5 and 6. And there you go. Just like that, 1 is done. Let's skip ahead a little bit here. Okay, let's do question 7. So in this case, we're trying to show not P arrow Q. Great. And then we'll list our premises. You can see we have P and we have not Q as premises. Okay, great. Well, the main operator in what we're trying to show is actually a negation symbol. So this is a pretty good indication that we're going to maybe want to do an indirect derivation. Because if we can assume, if P then Q, and force a contradiction, then we can do an indirect derivation and get not if P then Q, right? So let's do that. We want to show, or we want to assume, let's assume P arrow Q. And you can see from this, we will be able to get Q, right? Because we have P as a premise. So we get Q by modus ponens on 4 and 2. And then, oh, look at this. We've got ourselves a contradiction here already. On line 3, we have not Q. And on line 5 here, we have Q. Now you can access this not Q, even though it's earlier in the proof, because it's in the same layer of proof. If this was a nested derivation where we had opened another derivation above it, or sorry, let me rephrase. If this not Q was from a nested derivation above this Q that had been closed already, we could not access it. But because it's all part of the same level, we can access it just fine. So we can actually say we have an indirect derivation here. We've shown that if you assume if P then not Q, you get a contradiction between Q and not Q. So on lines 3 and 5. And you can see that confirms not if P then Q, right? Good. Yeah. So actually, this is a good moment to say something. The indents here matter a lot for knowing what lines you have access to. And because this is all on the same indent, we know we have access to it. And it's uninterrupted by a open proof or an open nested derivation that hasn't been closed. So it's all available. Great. Okay. Let's do question 8. We want to show S, right? So now we list our premises, copy and paste. I don't like the outside brackets, so I get rid of them. We say this is a premise. All right, good. So we want S. How are we going to get S? Well, we can see here that we can either modus tollens this line here to be able to get a not s. If we can show not if p then q, then we can use modus tollens to get the negation of this, which is not s. And from that, we could do a double negation elimination to get s, right? But also, if we had a p, if p then q, we could get a s just by a premise. Maybe what we should do actually to get this s is show that we can't have not s. Because if we can show that not s leads to a contradiction, we'll get not s, and we'll get a double negation elimination. So there's a few ways you could attack it. You should try a few, see where you get. You get a kind of a knack for these kinds of things after you do enough practice, and I'm feeling like showing not s will lead to problems as a good route. So let's try that. Let's assume, or let's show, here we'll open another line. Let's show not s, because if we can get not s, we're going to be in a good track to get s by just doing a double negation elimination. So let's open a new thing. We're trying to show not s, which is not in the proof anywhere, but let's see what we can do. Well, to do that, we might assume not s, right? And if this leads to a contradiction, then we're going to get not s. Well, we know from not s, we can get if p then q. Great. By modus ponens, right? Modus ponens on 5 and 2. Well, look at that. We have if p then q. And from our premise, we know we can get s from it by modus ponens, right? On 3 and 6. We have the left side right here, so we can get the right side by modus ponens. But look at that, there's a contradiction here. We have s and not s. So we know if you assume not s, you'll get a contradiction. So we can close our indirect demonstration with lines 5 and 7. There's a contradiction there. And now that we've closed this nested derivation we opened, we have access to what's here on line 4, which is great. So now we can get s by doing double negation elimination on line 4. We have this not s. We can eliminate the double negation on it and get just s. Well, that's exactly what we were trying to show is s. So fantastically, we have it right here. So we have a direct derivation on line 9. And look at that, the proof is complete. So knowing what to do, let's go back a little bit. Knowing what to do at this stage will take some trying things out. That's why I recommend you have a pencil and paper so you can see where different routes take you. But once you get the hang of it, you start to get a feel for what will work. Let's do another one. Here, let's do number 12 since it's the last one and it looks like it's full of fun and interesting things. So we write what we're trying to show, put an indent, and then list all our premises. And I forgot to say where I got this from. It's a premise. And then let's just copy and paste this instead of writing it out. Okay, good. So we want to show not Q. Well, if we assume Q and it leads to a contradiction, then we can get a lot of work going there. So what would happen if we assumed Q? If we assumed Q, we could get S, and then maybe we could, yes, I see what we could do. All right. So you can see we have a Q here. So if we assume Q, we'll get a S. And if we assume S, we can show that if R, then S. And then we'll get a P, which will let us show not Q, but that will contradict with Q, which we assumed, giving us an indirect derivation. So it's going to be many steps. So let's see where we go from here. So we want to show, or we want to, let's assume Q. Well, then we get S from modus ponens on 5 and 3, right? Now we want to get a P so that we can get this not Q and get a contradiction. But first we need to show that if R then S. So we're going to do a nested derivation. We want to show R gets us S. So we're going to do a nested derivation. We're going to assume R because we're doing a conditional derivation here. You know, you assume the left side, you get the right side. Conveniently, we have this S, which is earlier in the whole derivation and is not from an unclosed derivation, like an unclosed nested derivation. So we're good. So we have R, so then we get our conditional derivation on line 6, which we have access to. You can see it's nicely closed up here. So now we have access to this if R then S, which is fantastic because it can give us P. So then we have P by modus ponens on 7, where we now have access to this because we closed it, and 4. And this gives us not Q, because on line 2 we have if P then not Q. And here we have P, line 2 and 10. And then we have a, let's see, what do we have here? Here's what I should have done. So the problem here is that I have an assumption here that I need to close. So I should have introduced a, well, maybe this will work. Let's see. Yes, okay. So I was wrong. There was no problem. My apologies for confusing you. I had a little brain hiccup there. But you can see we got down to this not Q after assuming Q. And so we were able to close the proof that not Q wouldn't work because not Q contradicts with Q. These two are in contradiction. So we know that what we assumed to get down here, which was Q, leads to a contradiction, and so it can't be true. So we get not Q, which is what we were trying to show. So there you go. That one is a little complicated. I suggest you try it, walk through it yourself. It's important you get the practice and see how everything works yourself. So you have access to this practice document. Do it. Do all the ones that I didn't do as well, and you'll get a hang of things. Okay, and so with those examples, with everything explained, hopefully acceptably well, that's the end of chapters 5 and 6. That's the end of the lesson. Again, really keep up with the practice. Do the optional practice. It will help you a lot. Keep up your problem sets, and make sure you're looking at the due dates on the course calendar, because the homework has to be submitted. The problem sets have to be submitted pretty regularly. So please take a look. And yeah, again, just keep up with the practice problems. They'll help you a lot. And you really should be doing all this because on the midterm or the final, you will be able to submit incorrect answers. So you need to get the practice to know what you're doing. Okay. But yeah, just keep doing examples, doing the problem sets. Things will come if they aren't already. Just need to stick with it and ask questions to your TA or me at the live sessions. Yeah, so thank you, and I will see you in the next lesson.